Welcome to the deep dive. Today we're looking past the flames, really, into something critical in building fires.
Right. Not the fire itself, but how the smoke behaves, how it moves.
Exactly. How it moves, how it spreads, sometimes in ways you wouldn't expect. It's all physics, isn't it? Complex physics.
Uh-huh. And understanding that is absolutely key for safety. It governs how buildings are designed, how first responders operate. It's fundamental.
And we're digging into the gold standard source here, the ASHRAE Handbook of Smoke Control Engineering.
That's the one. It lays out the principles we rely on.
So our mission today, let's unpack the 6 key factors driving that smoke movement. Turn this engineering insight into something everyone can grasp.
Sounds good. These 6 are expansion, buoyancy, HVAC systems, what's called the elevator piston effect, the stack effect, and finally, wind forces.
6 big ones. Where do we start? Right at the source.
Let's start right where the fire begins, with the physics of the smoke itself.
Okay, factor 1, expansion. Now, if you picture a fire, you see this huge cloud of smoke, right? But you're saying that cloud isn't mostly smoke.
That's the surprising part, yeah. The actual volume of gas from the burning stuff, relatively small. But the heat is intense, and that heat drives something called entrainment.
Entrainment, like it's pulling things in.
Exactly like that. Think of a hot plume rising fast. It creates a sort of vacuum around it, sucking in huge amounts of the cooler air nearby.
So the plume gets bigger and bigger because it's mixing with the surrounding air.
Massively bigger. That's where most of the volume comes from, entrained air.
But the original gases are also expanding from the heat itself, aren't they?
Oh, absolutely. That's the initial kick, the thermal expansion. And it's dramatic. The handbook points out, at really high fire temperatures, say 2200 Fahrenheit, that's about 12,260 Celsius,
Yeah.
those gases can expand to about 500% of their original volume.
500%, just from the heat.
Just from the heat. It's incredible pressure.
So what does that mean for the room the fire's in?
It means the room gets pressurized almost instantly. Forget waiting for vents. That pressure forces the hot smoke and toxic gases out, through every crack, under doors, into hallways, anywhere it can go.
So containment is tough right from the start because the volume just explodes outwards.
Exactly. Expansion is the first powerful engine pushing smoke out of the fire area.
Okay, that makes sense. If expansion pushes it out, what about factor 2? Buoyancy. That's the classic smoke rising thing, right?
That's the one everyone knows. Hot air, hot smoke, is less dense than the cooler air around it, so it floats upwards.
It rises towards the ceiling.
Right. And there's a measurable force behind it. It's small, maybe around 16 pascals or, let's see, 0.064 inches of water gauge.
16 pascals. That sounds tiny. Why even mention such a small pressure?
It is tiny, but it's constant. Think of it like a very, very gentle push upwards over the whole area of the smoke plume. It's enough force to keep that hot smoke layer stratified up high against the ceiling as long as it stays hot.
As long as it stays hot. That sounds like the catch.
It is, because smoke doesn't stay hot forever once it starts moving away from the fire.
And this leads to the danger of cool smoke.
Exactly, and this is maybe one of the most critical, often misunderstood aspects. As that smoke travels down hallways, mixes with more air, maybe goes through HVAC systems, it cools down. It can reach ambient room temperature.
And when it cools, the buoyancy goes away.
Completely. That upward lift, gone. Now its density is close to regular air.
So, what does it do then? Just hang there?
It can. Or worse, its movement becomes totally unpredictable. It's not driven upwards anymore. It can stagnate, pool in areas, or even start throwing along the floor.
Along the floor? That sounds really bad for people trying to escape.
It's fundamentally different and much more dangerous in some way than hot smoke.
How so?
Well, hot smoke rises. Yes, it's deadly hot, but it often leaves a clearer layer near the floor, at least initially, where people might crawl. Cool smoke doesn't do that. It can fill the space from the floor up, drastically cutting visibility right where people are walking or crawling.
And I guess standard smoke detectors up on the ceiling might miss it for longer.
They absolutely can, yeah. If the smoke isn't hot enough to rise strongly, those high-level detectors won't pick it up as quickly. So you get this blinding, toxic condition spreading at breathing level before the alarms are fully triggered or systems react. It's a nightmare scenario.
Wow. Okay, that shift from predictable rising smoke to unpredictable cool smoke is huge. Let's move from the smoke's physics to how the building itself plays a role. Factor 3. HVAC systems. Heating, ventilation, air conditioning. Friend or foe?
Definitely a double-edged sword. Those ducts are designed to move air everywhere, right?
Right. Efficiently.
So if a fire starts
Yeah.
and the HVAC system keeps running, It becomes a perfect distribution network for smoke.
Spreading it far beyond the fire zone.
Very far and very fast, unless it's designed to shut down or switch into a smoke control mode.
Are there specific parts of the HVAC system that are particularly risky? The handbook must highlight some areas.
Oh yes, the big danger point. Vertical duct shaft.
The main risers connecting floors.
Exactly. Think about it. It's an open channel going straight up, sometimes many stories. Hot smoke gets into one of those, and it can shoot up to much higher floors with very little cooling happening along the way.
So someone on floor 20 could be breathing smoke from a fire way down on floor 5 just because of a duct.
It's entirely possible, yes. That's a major pathway for rapid vertical spread.
So how do engineers fight that? What are the countermeasures?
It's usually a layered approach. First, smoke detectors tied into the system to trigger immediate shutdown of fans or specific zones. Second, passive barriers, fire dampers, smoke dampers. These are designed to physically close and seal the ductwork when heat or smoke is detected.
Like a gate closing off the pathway.
Precisely. And then in more complex buildings, especially high-rises, you have active smoke control systems. These use fans to pressurize areas around the fire zone, pushing air out to keep smoke in, or they might specifically exhaust the smoke zone.
Okay, so HVAC is a major factor. What about factor 4? This one sounds weird. The elevator piston effect, a plunger.
The plunger analogy is actually pretty good. Picture the elevator cab moving up or down in its shaft, the hoistway.
Okay.
The hoistway is basically a sealed tube, or close to it. The moving cab acts just like a piston in a cylinder. It pushes air ahead of it and pulls air behind it.
So if it's going up, it's creating high pressure above it and low pressure, like a vacuum, below it.
Exactly that. And those pressure differences can be surprisingly strong.
Strong enough to matter in a fire. How?
Definitely strong enough. That positive pressure above the car, it can force smoke out of the shaft onto upper floors, maybe through elevator door gaps. And the negative pressure below, that can suck smoke into the shaft from a lower floor where the fire might be.
So the elevator shaft itself becomes contaminated, potentially spreading smoke vertically.
Yes, turning the whole shaft into a chimney and potentially making elevator lobbies on multiple floors dangerous.
Do we know how much pressure we're talking about? Is it significant compared to, say, buoyancy?
Oh, it can be much more significant than buoyancy. Studies cited in the sources show it can generate up to 30 pascals of pressure difference, maybe even more in some cases.
30 pascals? No, wait, you said buoyancy was around 16 pas, so this is potentially double that.
Easily double, yes. And remember, 30 pascals is often the target pressure difference that smoke control systems are designed to maintain to keep smoke out of safe areas like stairwells.
So the elevator moving could actually create enough for pressure to overcome the safety systems or make doors hard to open.
It absolutely can, yes. It can compromise the seals on fire doors, push smoke past barriers.
Yeah.
It's a major complicating factor.
What makes it worse? Faster elevators, tighter shafts.
Both. Faster cabs create stronger pressure pulses, and single cab hoistways are generally worse than, say, a bank of elevators sharing a larger hoistway because there's less volume for the pressure to dissipate into. Leakage around doors is also a huge variable.
So engineers have to account for this piston effect when designing smoke control around elevator cores.
They have to. This often leads to things like pressurized elevator lobbies, special ventilation for the hoistway itself, or carefully designed venting systems. It's complex.
Okay, that's fascinating. We've done the fire's expansion, its buoyancy, the building's HVAC, and now elevators acting like pistons. Let's move to factor 5, the stack effect. This feels like it's mainly about tall buildings.
Primarily, yes. The taller the building, the more pronounced the stack effect becomes. It's a natural phenomenon driven purely by temperature differences between inside and outside air.
Like a chimney.
Exactly like a giant chimney, or sometimes an anti-chimney. It creates a continuous flow of air up or down through all the vertical openings, stairwells, elevator shafts, service ducts.
You feel it sometimes, right? Opening a lobby door in winter in a tall building and getting that blast of cold air rushing in.
That's it perfectly. That's the classic stack effect in cold weather. The building is warmer inside than outside. That warm, less dense air wants to rise. It leaks out through openings high up in the building. To replace that escaping air, cold, denser outside air is drawn in forcefully through openings at the bottom. That's the rush you feel.
And the opposite happens in summer, if it's hot outside and cool inside.
Yep, then you get the reverse stack effect. The cool, dense indoor air sinks and flows out through lower openings, and warmer, lighter outside air gets drawn in through openings higher up.
So this creates a constant, natural airflow pattern throughout the building's core. How does that influence smoke movement during a fire?
It's often the dominant force, especially in high-rises. It can completely overwhelm buoyancy or even some mechanical systems. Think about that cold weather scenario again. Strong upward flow. If you have a fire on a lower floor,
The stack effect will just suck that smoke straight up the shafts.
aggressively. It acts like a supercharger for vertical smoke spread. Conversely, if the fire is high up, the same effect might actually help contain it by pulling air downwards from above. The location of the fire relative to the building's neutral pressure plane, the level where inside and outside pressures are equal, is absolutely critical.
So designers have to know where that plane is likely to be in different seasons and factor that into their smoke control strategy.
They do. Stack effect calculations are fundamental for high-rise design.
Okay, that brings us to the final factor, the one that seems maybe the hardest to predict. Factor 6, wind forces.
Wind is definitely the wild card. It acts on the outside of the building, creating pressure zones.
How so? Like hitting one side harder?
Exactly. The wind hits the windward side experiences positive pressure. Air is being pushed against it. The other sides, and especially the downwind side, the leeward side, experience negative pressure or suction.
And these outside pressures affect the inside.
They absolutely do. They can drive air infiltration or exfiltration through any leak in the building, envelope windows, doors, vents. This external pressure field competes directly with the internal pressures we've talked about, like stack effect or HVAC pressurization. A strong wind can completely change the game.
But wind is constantly changing speed and direction. How can engineers possibly design for that? Do they just use worst-case scenarios?
That's the challenge. You can't predict the exact gust at the moment a fire breaks out.
Uh-huh.
So engineers have to work with, well, average values or statistically likely maximums for that specific location.
Average values. That sounds a bit risky if a sudden gale could compromise everything.
It's a calculated risk based on meteorological data and often wind tunnel testing on models of the building and its surroundings. You design for a reasonable worst case, not necessarily a hurricane hitting at the precise wrong moment. But you need to understand the key variables influencing wind's impact, which are, first, obviously wind velocity. Faster wind means much greater pressure. The force increases with the square of the velocity, so doubling the wind speed quadruples the force.
Okay, speed matters a lot. What else?
Second, the ground effect. Wind speeds are generally much lower near the ground because of friction, buildings, trees, etc. But get higher up, a tall building, and the wind is much stronger and more consistent.
So the impact is worse on the upper floors of a skyscraper?
Typically, yes. And third, critically, surrounding structures. Another nearby tall building can completely alter the wind patterns. It might shield your building, or it might funnel the wind, creating even higher localized speeds and pressures right where you don't want them.
So predicting wind pressure isn't just about the weather forecast, it's about the building's specific urban environment.
Absolutely. It requires detailed analysis.
Okay, let's recap. We've journeyed through these 6 key factors. Started with the fire itself, expansion forcing smoke out, buoyancy lifting hot smoke but hiding the danger of unpredictable cool smoke. Then we hit the building systems, HVAC ducts acting as potential highways, and elevators creating those powerful piston effect pressures.
Right.
And finally, the big environmental drivers, the relentless stack effect in tall structures, and the unpredictable force of wind.
That's the landscape. Those are the forces smoke control engineers are constantly battling.
So pulling it all together, what's the main takeaway for someone trying to understand building fire safety?
I think the main takeaway is that effective smoke control isn't simple. It's not just about putting out the fire. It's about deeply understanding and managing these 6 interacting physical forces to keep pathways clear for people to escape and for firefighters to get in. You have to consider all of them together.
It really highlights how physics, engineering, and human safety are completely intertwined in these structures we live and work in. We touched on that danger of cool smoke flowing low while hot smoke is high. Here's a final thought to ponder. If you have both conditions potentially happening in different parts of a large building during the same fire, how do you design one evacuation plan? How do signage, procedures, and system designs account for needing to maybe crawl low in one area because of cool smoke, but stay upright or find shelter from heat radiation elsewhere? That dual threat seems incredibly complex to manage for occupants.
It is incredibly complex, and that complexity is precisely why modern codes are pushing towards more robust, often actively pressurized systems, systems designed to fight back against all these forces and maintain a tenable environment, regardless of whether the smoke is hot or cool. It's about buying time.
A fascinating and vital look beneath the surface of fire safety. Thanks for breaking down these complex factors for us. Keep asking questions, keep learning. We'll catch you on the next deep dive.